So again, this code says very simply that if all these situations are met, we're going to call collide with cell. We're going to take the player and try to collide with one of those boxes of the 400 boxes that make up our maze. Collide with cell. Player and X and Y, that's the actual box that we collide with. So this calculation just takes our map array bounding box for our thing and adds player radius or subtracts player radius, as you can see, and finds the absolute bounds of our collision for the cell. Lx and Lz, that's least x and least z, and mx and mz, that is most x and most z. And then we actually look at those values and double check. Are we really overlapping? And if we're not overlapping, just bomb out of this function. There's no need to go any further. Okay, so we know we really are in the same column as this collision box. We may be too high, we may be too low, but we know that this is the collision column we're actually working with. And here's where we actually get our height value. And this is really simple. We say if position y is greater than height minus 30. So it says if, remember my player is a dot. My player is a dot, and my player position is a single dot in space, and y is up and down. Here's the height, the top of my box. And I'm going to go down 30. What I'm saying here is if I'm in that zone, first off, if I'm in the zone of being somewhere penetrating the box, or at least above the box, but I'm no further than 30 down from the top of the box. I may be inside the box, but no more than 30. Then I should really be on top of the box. But of course, this code just double checks that I really am in the box. So this whole code just says, if I'm stepping on the box and I'm not too far inside the box, if I'm not up to my ankles or up to my knees or whatever, then go ahead and boop, push me to the top of the box. What does this say? This means that there are 6 sides of the box, and the most important one, the first one we check, is the top of the box to say, if you're sinking into the box but you're in the box, go ahead and push yourself out. This helps us jump onto a box. If we jump on a box but we didn't really quite hit the box, then it pushes us up to be the top of the box. But of course, if we didn't jump high enough, then something else is going to happen. And that high enough is 30 below the top of the box, according to this code. Okay. So best dist is a function, is a value of, a distance, right? Best distance, best position, and dist to side. This is all setup variables so that we can check four sides of the box. And the whole thing of what this code is simply doing is saying, how far am I towards one of the sides of the box? And remember, and this is what's kind of cool and makes it a little easier to control, the boxes we're using, both visually and as collision boxes, are axially aligned. They're axis-aligned bounding boxes, sometimes called AABB. But axis-aligned bounding boxes means that the walls are actually aligned with the axes of the world in X, Y, and Z directions. So that gives us the flexibility to say, well, are we close to this wall? By a simple check of the X value, is X greater than, or is Y less than, or is Z the same as? Axis-aligned bounding boxes, when we can get away with using them, are a fairly cheap and easy way to do collision detection. And here we're detecting to find out which of the four sides of the box we're closest to. Once we get that information, we actually push ourselves out to that side of the box. And by the way, if we've gotten that far, that is to say, if we've bumped into a wall and been pushed back, then this code that I've highlighted says, let's go through all the doors and see if there's a closed door that we've actually hit, start moving the door down. All right, and finally here at the bottom of map is our actual draw mesh function, which we've talked about before. It just wraps up all the code that draws the mesh, and you just pass in the model and the world matrix, and boom, you've got a drawn mesh. So we've looked at game1.cs and how it's a framework for the rest of the game. We've looked at how much work we do in map.cs. We do a whole lot of work in map.cs. And specifically our work is in not only drawing the world, but in building the structures necessary to make the collision happen, and then actually going through and making the collision happen on a function that takes player as an argument. And in the meantime, of course, because we have that door functionality, we have a little .cs called doorState.cs, which is just a very simple class that contains 3 values. So the one thing we really haven't looked at yet is player.cs. Let's look at that now. Remember that player.cs, or the player objects player list gets created, and then the player object gets created and added to the list in game1.cs. And of course, the update gets called. So here's player, in namespace FPSBoxy, we have a player. And the first thing is the static public list of players. So that's where our list is. It happens to be a static member of player, which basically means we just say player.list whenever we're talking about that particular list. And then here's height equals 50. And that is exactly what it means. And we've been talking about how our avatar is just a dot in space. And of course our avatar is a camera on an invisible stick above the floor. So how long is that invisible stick? Right here, it's 50. And we know that boxes happen to be 100. Our eye height for our avatar is half the size of a box that makes up our world. And then our player has several other variables. We have an isDead flag that we're not using because this game does not currently allow you to die. We've got position and velocity. That's of course 3 space position and 3 space velocity. And we've got yaw and pitch. Remember, yaw is turning this way, turning around the y-axis. Pitch is up and down. It's turning around the x-axis. And remember, our last of our yaw, pitch, and roll. Roll must of course be around our z-axis. Roll is like that. So pitch, roll, yaw. And then we've got, oh, look at that. I knew we had to have 3 matrices somewhere. And here it is, our 3 matrices. Notice again that it's static and public, meaning that we say player.projection matrix and camera.projection matrix and look matrix. Why do we have a look matrix? Well, anyways, you know that we have 3 matrices that we always have to use to make 3D games. And we'll find out how these matrices work that we actually added to the player. So here's our constructor for our player. Start with a velocity of 0, looking yaw and pitch 0, not dead, and a new position. The new position is 133 in the x direction, 0 in the y direction, 155 in the z direction. And it says here start near the upper left corner, and that means of the map. Okay, here's our update. But before we go to the update function, I want to skip ahead. Notice draw. Yep, just like I called it, we're not drawing anything for the player because all we're really doing is positioning the camera. So, and we have a function that is called take damage. Well, when you actually are shooting things in your game, a take damage function is actually a very useful thing to have. But again, we haven't gotten that far. And now we have something we've almost certainly seen before in the 2D projects that we've done in this series. An update all function, a draw all function, and a clear list function. So, the update all function, the draw all function is really simple. It just calls the draw on each of the objects, in this case players, and we know that those draw functions are empty. So this whole draw all function doesn't really do much of anything, though it probably will in the future if we keep working on this code. Update all is a little bit more complicated, but we've still seen this before. All we're doing is calling update on each object in the list again, a player. And then we're walking backwards through the list, checking the isDead flag and removing them. Why do we do it in this way? The reason we do it in this way is because when you have an object-oriented game where you have lots of bullets and players and enemies and clouds and targets or whatever objects you have floating around in your world, and you want some of them to go away, it's actually not a good idea in the programming language to tell them to delete themselves. So we just get around that. We just have a flag that says, I'm ready to be deleted. It's called isDead. And after we update everybody, we go and check their isDead flag. Are they ready to be deleted? We will grant their wish. So that's a way for us to delete the objects in the list without having the objects responsible for deleting themselves. So this update all basically just calls the update function. So let's go back to the update function and examine what it is we're doing here in our player update function. What are we doing? We're getting the current state of the mouse and the keyboard, which is important because we're both looking around with the mouse and we're moving with the WSAD keys, the so-called WASD keys. And then here is our code for handling the mouse. Now, the problem with the mouse, at least on this Windows machine, is that when we ask Windows, where's the mouse? It tells us relative to the screen. In other words, if we move the mouse all the way up to the corner, we're flipped here, so I guess it's this corner for you. This corner right here is always 0, 0. And if our screen is, I don't know, 1000 by 900, then 1000 by 900, 1000x and 900y is right there. That's the dimensions of the screen you're looking at. And it all starts here in the upper left corner. So that's how Windows will give you the data of the mouse pointer. But that's kind of a problem in first-person shooter games because you want to be able to move the mouse left and right continuously. You want to be able to spin around as many times as you want. But we know that once the mouse gets to this edge or this edge, it's going to stop. So what do we do about this? Well, depending on the system, there are definitely different ways to do this. And depending on the library you use, you could theoretically get something called relative coordinates or absolute coordinates. And this mouse that I'm using, all it really does is continuously tells the computer how far it's moved in which direction. So there's lots of different possible ways that you can munch this mouse data into something usable for a first-person shooter. The way we're going to do it in this particular project is really simple. We hold on to the last position of the mouse pointer. We look at the current position of the mouse pointer. The difference is how far the mouse has moved, and after we check this, we actually force the mouse back to the center. And we keep doing that. We just force the mouse back to the center. This is great because it allows us to use the mouse like we're supposed to in a so-called first-person shooter. We're supposed to continuously move it around and look up and look left and look right as much as we want without the mouse coming to a stop. But it's not how a windowed environment on Windows is supposed to work. And that's where this code here, where you see is not key down F4 comes into place. Because what we're doing with this code, mouse position set 200, 200, is we're capturing the mouse. We're holding on to it and we're refusing to let you use the mouse as you normally would on the screen. We're using our mouse for our own purposes. This can get kind of a clunky, kind of a what the hey, especially if you want to use your mouse to click on the close button on your application. So in this particular case, we can stop the use of the mouse by holding down the F4 key. It's a key that's not usually used on the PC. So if you just hold it down, then your mouse works normally. Unless, if you're not holding it down, then the mouse gets captured by our application for our own nefarious purposes. Alright, so we see how we're using the mouse here to adjust yaw and pitch. Remember, yaw and pitch of our mouse. But now here's where we use the WASD keys, and it's really simple. We've done this kind of thing before. If the key is down, then move. Move how? Well, it's actually kind of cool. Look inside this WASD W, which is for forward. This W is, you push the key W, you're supposed to go forward. But where is forward? Forward is relative to your camera, or specifically relative to your yaw and pitch. How do we do that? Well, turns out our look matrix can contain our yaw and our pitch, and we will actually set that. But what we're actually going to do is we're going to take this value direction, which is 0 in the x direction, 0 in the y direction, and -1 in the z direction. And we're going to transform it by the inversion of the look matrix. In other words, we're going to transform it to where we're looking. And as you can see, the last line of this particular piece of code says velocity plus equals direction times 0.1. In other words, we take that direction and we divide it by 10, essentially, because we don't want to go too fast. And of course, if you change that number, we might go faster or slower. So these three lines basically here say we want to go forward. What's forward? Well, we found forward. If we found the direction of forward, we go direction in that. So, and the rest of them do basically the same thing. You can see that the direction of right is -1, 0, 0, and left is +1, 0, 0, and so forth. We take a direction in space and transform it, literally transform the 3D vector by the matrix of our look matrix, and we actually get a new direction to go in. This is how we're actually able to drive using the WASD keys. And then what does this code do? 2 lines, real simple. We take the velocity and go down, and then we take velocity as a whole and slow it down and multiply it by 0.95, which is, these 2 lines basically do gravity and friction. And they're real simple and easy and simplistic ways of doing physics in games. And then here we go, position equals position plus velocity. This allows us to accelerate from a stop and to slow down to a stop. And then incidentally, I just have a piece of code here, real simple, that says you cannot fall through the floor forever. You could fall through the floor theoretically. I'm just going to stop you at 0. I don't want anybody falling past the world. So if your y is less than 0, bump you back up to 0. And then, hey, we've seen that function, map collide. So there you go, we're colliding with the map and, you know, hopefully bouncing off of walls or standing on top of walls as necessary. So notice we're actually making 2 matrices at the end of our update function. The first one is look matrix, and remember I told you the look matrix was just a matrix composed of yaw and pitch, and that's exactly what it is. Look at this line. It's simple. Look matrix equals create rotate y, yaw, and create rotate x, pitch. And then what is our camera matrix? Our camera matrix is basically a look matrix multiplied by a translation matrix. What are we doing here? We're saying position, that's actually the position of our dot of our avatar, our player, which is, you know, the foot, the dot of the foot of our avatar. We, for some reason, multiply it by -1, and we subtract a vector 3 eye height. Remember what eye height was? We set it to 50, which was half the size of a block. So camera matrix, the actual camera matrix, one of the 3 major matrices we need, is set here at the bottom of the player update. So every time through player update, we're recalculating where player is. I'm sorry, where the camera is. And we happen to also be calculating look matrix, which is great for figuring out how we're moving relative to how we're looking. Okay, that's the sum total of our update function. So let me fire up the game and look around. Notice I'm using this mouse button to look around. I'm using the mouse to look around. You can see up there the sky. You can also see that I can only go so high. Why can't I go any higher? Let's go back to the code and look. Here we go. clamp pitch so you can't look at your toes. This is at the top or near the top of the update function for player. It says pitch equals math helper clamp. Remember, that means that you have a value, a low value and a high value, and it forces the value to be between those two values. And the low value is -7, and the positive value is +7. So this pitch, no matter how it gets changed by the mouse value, is going to stay within that range. And that is why, as I hit the F5 again, that is why I can only look so far up and so far down. I cannot actually look at my toes or look directly above me. And of course this also means, which would really throw you for a loop, it doesn't mean that I can push my pitch so far that I actually start looking backwards, which kind of is not what you want in a first-person shooter anyway. So I can look up, I can look down, I can look at the skybox, I can look all around, and I can press the W key and it moves me forward, but forward is relative to my camera. In fact, if I point myself up far enough, then the gravity is weak enough, then I wind up flying. See, gravity is slowly pulling me back down to so-called Earth. But we know that it's not so-called Earth. We know that this floor we're looking at is not one big monolithic floor. It's just a bunch of big boxes that are at the 0 position, the lowest height position, and I am walking on them. And because remember we saw in the map that section that showed that we had a ladder or a stair step? Well, here's our stair step when we can walk up it. Now, how can we walk up it? And you see it walks with quite a jerk. We're going down it, of course, because of gravity, but we walk up it because our collision resolution said the first thing we check is the top of the block. And if that top of the block, if we're inside the top of the block, but we're within 30 of the top, go ahead and assume that we're standing on the block. And so each of these little stair steps must be less than or equal to 30. And they are, which is why I can walk on top of the block. And then of course once I actually fall off the block, that gravity really is quite weak. And I try to walk back onto the block. Nope, I am too low. I cannot walk onto the block. I am bouncing off the side of the block. It's forcing me. But you know, some blocks are different from others. That's a door block, and when I bump into it, it activates the dropping of the block. And now because that is less than 30, I can step on that block. So I will do a separate video about this, the 3D particles. And right now the particles kind of look static because they're just a beam straight up into the air, but I assure you they're actually quite dynamic. It's a continuous explosion of particles going straight up. And if we adjust it a little bit, we can see some interesting behaviors on those particles. So that is it. That is our world. That is our 3D space. And of course, if we fly up, we can look at the rest of the world, see the whole world, and we could even fall off the edge of the map. But remember, I just showed you the piece of code that said that no matter how far away from the world we get, we're never going to get below 0 in the Y direction. That's what's going on here. We're stuck. Well, actually, now we're stuck at 0Y. Alright, normally in these videos I like to talk about all the possible things that we could do to upgrade this application that I've given you. Upgrade this set of code that I've given you. And today is no different, but I'm going to burn through it reasonably quickly so that we don't waste anybody's time. Alright, I would like you maybe to change the skybox to have seamless textures. Right now the skybox is kind of ugly because it's got those corners and edges on it. Fix it. I'd like you to change the dimensions of the maze, both of them. Right now it's 20 by 20, it's 400 blocks. You can do better. In fact, your computer probably can do better. Try 800, try 1000, try 5 by 5. I don't know, that's a chunky world, but make some change. Here's another one. Change a wall texture, including the top and bottom textures. So by that I mean that we have to see a different texture on the sides of the block and on the top and on the bottom of the block that make up, one of the block boxes that make up the world. Okay, so you see those white lines in the distance on the map. Those could be fixed, and they're an artifact of a particular way that 3D gets done on video games. So that probably ought to be fixed as well. Here's another thing, change the maze significantly. Right now I've got the little maze with the doors clustered in the thing and the little ramp. Change it, make a new maze for me that I can explore. Okay. Now not only that, but it'd be nice to see if you could make the maze a little more interesting. In other words, make it so that the doors are in strategically important positions, so that if I can, the only way that I can get to the edge of the end of the maze is by going through the doors. And you know what? We just said it was 5 doors. Why not have 10 doors? Why not have 2 doors? Let's change the number of doors. Okay, now we've got a bunch of particle streams, green particle streams coming up from each of the doors. Change the color. Also, the streams all go vertically. It'd be nice if they were in a spray. So change the velocity of the particles that come from the doors. Okay, so particles are intended to, be created in space and then fade out over time. You could theoretically really impress me by making a particle emitter on the nose of the player, or actually not on the nose, but like 50. Let's just say 50 units in front of the player, wherever the player is looking. Put a spray of particles. All right. How about making the player move faster? How about inhibiting flying and adding jumping? That's the thing is, you go up, you fly. We could inhibit that, but it'd be, normally in a first-person shooter you don't fly, but you jump. So let's put that in. So add a key that toggles a mode that lets you see high above the maze looking down. This would be great for when you're creating the maze and you're adjusting the maze to your liking. So all I'm saying is hold down a key, and suddenly you're not looking from the player's point of view anymore. You're looking from high above the maze. Try that. Okay, so we showed the camera pitch limits at like 0.7 to 0 to negative 0.7. Change that. Change it so that the player can see more up and more down. So right now there are only 2 texture blocks in your maze. There's the normal wall block and then there's the movable door block. I'd like to see 4 different textured blocks instead of 2 being used in your maze. So, I mean, most first-person shooter games have sounds. How about footstep sounds? When you move forward, you go tick, 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 tick. That'd be great, wouldn't it? Let's have footstep sounds in the game. And while we're doing sounds, there are a couple other sounds that seem very logical to me. One would be the door movement, the door opening sound, and one would be where you jump and you land. Then when you land, there's a sound of jumping. All right, so you've seen how this very early and very simple first-person shooter kind of presentation game that doesn't really have any shooting, doesn't have a gun, but it has a maze to run around in. You've seen how it works, and I'm excited to see what you come up with and how you build upon this basic set of code that I've given you. As always, have fun, and I'll see you next time. Bye-bye.